Hello everyone. So again welcome back to the latest lecture session. Again a quick recap of what we have been up to. So in the context of remediating contaminated groundwater, we have been looking at extracting the groundwater or pumping the groundwater out and then treating it. So in that context we looked at the ideal case scenario, as in what's obviously the ideal case scenario. I would be able to finish my pumping or extracting the relevant contaminant, let's say, when I pump out just the contaminated plume, let's say, or the contaminated groundwater. But as we have looked at in the previous class, we know that there are different phases and thus different sources of contaminant. So in pump and treat or extraction of the relevant plume, I am only pumping the groundwater out, as in only that contaminant in the aqueous phase or in the groundwater will be removed now, right. So obviously if the contaminant is adsorbed onto the soil or the organic fraction of the soil, or is present in its own phase as non-aqueous phase, let's say, obviously they are going to act as reservoirs of this particular contaminant. So as I remove the contaminant from the groundwater, let's say, again contaminant from these particular or two reservoirs that we have talked about, or the phases, they are going to, what do we say, either desorb or let's say through diffusion change phase into the aqueous phase, and again you are going to have concentrations of these contaminants above the relevant cleanup standards, I guess, right. So that is something we looked at, and we looked at a few other aspects too, as in stratification, I believe, right, as in I have sand, clay and gravel and so on. So obviously the groundwater flow velocities through these particular layers is going to be different, right, and thus let us say only that contaminant that is in that particular zone where the hydraulic conductivity and thus the groundwater flow velocity being relatively high, right, only that will be, or that will be removed first. And again you need to have equilibrium, as in the contaminant in the clay layer needs to diffuse into the sand layer and then it is going to be removed. So obviously pump and treat might not work well if you have stratified layers, and also the contaminant has, what do we say, reached equilibrium between the different strata here, right. So that is one particular case we looked at. And what have we looked at until now? We have looked at issues with respect to tailing and rebound, right. And in that context, what are some of the cases or causes? Let us say we know that the presence of D-NaPl or L-NaPl can act as reservoirs, let us say, and in that context obviously we know that it can be present in its different phase or adsorbed onto the relevant what do you say, organic fraction of soil, right, say, right. And then also we have different strata or stratification, that is something we looked at, right. So let us just continue this particular discussion for a couple of minutes and then move on to calculating, let us say, the time required or estimating the time required for this particular, removing this particular contaminant, right. So let us look at what we have. So similar to what we had earlier, let us say when we had a non-aqueous phase liquid, let us say in between soil particles, let us say this is the non-aqueous phase liquid and this is the soil, right, and again compound adsorbed onto the soil, and this is the groundwater here. So two sources, as in from the NaPl and also from the soil, let us say. Here let us say we have another case, as in where we have a solid precipitate, let us say, as in different forms of chromium, let us say they can precipitate out, let us say, right, as in the contaminant can either be in the aqueous phase or in the solid phase by itself. So here let us say if I have a case where it is in the solid phase, right, and here that is what I have. So here I have let us say this is the case when I had all the three phases earlier. So here obviously it is not NaPl, but I have the solid phase here, solid phase and the aqueous phase, right. Earlier it was the case of NaPl phase, soil adsorbed onto the soil, and the aqueous phase. There I had three phases and here I have two phases, right. But the principles are similar, as in that instead of partitioning between the non-aqueous phase liquid and the water or the aqueous phase, right, the compound from the non-aqueous phase liquid will what do we say, diffuse into the water, right. So here now I have a solid particle, let us say, or the solid contaminant in its solid phase, and that again will dissolve, right, precipitation and dissolution. So obviously let us say if the soil particle is out here and if I have groundwater surrounding this, let us say, and obviously depending upon solubility, solubility will give me an idea about the maximum concentration that that particular contaminant will be present in that solution, let us say. So, let us say equilibrium has been reached, and the solution around this soil particle, let us say, has the maximum solubility, or the solubility, pardon me, or is it the solubility concentration, right. And obviously now if I remove this water, let us say, and now I have fresh water around this particular soil particle, not soil particle, pardon me, solid phase of the contaminant. Now again I am going to have dissolution of this particular solid phase, right. Why is that? Because the water surrounding this particular solid phase of the contaminant does not have any what do we say, contaminant, right. So, the equilibrium has not been reached. So, now again the system is going to change or move in such a direction that there will be equilibrium between the solid phase and the aqueous phase, right. So, the compound is going to dissolve from the solid phase into the aqueous phase, and that is what we see here, I guess. So, initially let us say I keep pumping out all the water in the aqueous phase, and here I have pumping or duration, pumping duration or volume pumped obviously, and relative concentration here. So, initially I pump it out here, right, and thus I see a drop in the relevant concentration here, but relevant concentration of the compound as an, so I might presume that I am done with my particular cleanup here, but I see that it does not reach 0 though, it continues at a particular, the concentration does not drop below a particular value here, for a considerable period of duration or period of pumping now. Why is that? So, initially I see a tailing, not tailing, pardon me, a rapid decrease in the concentration, that is when all the, let us say, compound in the aqueous phase has been removed. But then for a considerable portion of this particular pumping, let us say, or for even after particular or considerable volume of the relevant groundwater has been removed, I see that, I am talking about this phase, the concentration does not change, right. Why is that? Because we have a solid phase, and there you see the relevant precipitation, not precipitation, pardon me, dissolution of the solid phase into the aqueous phase, right, change in phase from the solid phase into the aqueous phase, and that is what you see here. And then once all the solid phase has precipitated out, so let us say initially I had a bigger chunk of particle, let us say, obviously I am not going to have what do we say, a few millimeter size or diameter particle, microns or such, let us say, depending upon again the type of what do we say, conditions there. Let us say the solid particle size can vary from different from one size to the other, right. So, again if I have a solid particle initially now here, and then water out here, I keep removing the water, again equilibrium keeps shifting, and so slowly but surely this particular solid phase the particle will precipitate, right, pardon me, dissolve. So, then the phase of this or the size of this particle is going to keep decreasing, right. So, that is what I would or one would presume happens out here, and when all the particular solid particle has dissolved, then I am going to see a further decrease of the particular contaminant concentration in the groundwater, right. So, again similar to the NaPl or the non-aqueous phase liquid, here we have a solid particle and then the relevant aspects here, right. So, the other aspect is that when we would have issues with what do we say, tailing, let us say, is that I am pumping the water out. This is my location of the well, right, let us say from Havendel et al, and this is the boundary of my particular flow line for that particular extraction well, let us say, right. So, but as you know though, in the center, along the center, let us say the groundwater flow or the velocity would be relatively fast and relatively moderate as we move away from that, and obviously remarkably or relatively slower, and also the paths that the groundwater particle or the aqueous molecule should take would be greater along the periphery obviously, right. So, obviously relatively slower at the periphery, let us say, of this particular flow path, and moderate and then fast through the center, right. So, again this will cause issues with respect to tailing, and that is what you see here. So, here I have the relevant dissolved concentration and pumping duration of or volume pumped. So, why do I see this tailing now? Because there are different flow velocities within this particular captured plume here, right. Again we have more what do we say, faster what do we say, moving groundwater in the center and less faster in the along the periphery. So, obviously the contaminant in the center of the plume will, let us say, be pumped out first, but you still have contaminant along the periphery, and that obviously as we see here takes longer to be pumped out, and thus you see this particular behavior of tailing here, right. And let us move on to the relevant aspects here. And again this is one other aspect where we have LNAPL, let us say, right. So, we have LNAPL and here we have a case of zone of residuals, I guess, right. So, think of this case LNAPL or light non-aqueous phase liquid, right. It is non-aqueous phase, right, it is present as a non-aqueous phase, let us say, but the key is that it is light or relatively lighter than water, right, it is not denser than water. So, obviously it would float above this particular or stay at the top of this particular groundwater table or be in contact with the upper portion of this groundwater now. And maybe if anything, obviously if it is soluble, some of it will also be soluble, obviously, right. So, let us say if I detect the concentrations, let us say of this particular NaPl in the groundwater and I start pumping groundwater out, right, and then I have a cone of depression, I pump that water out, okay, and then I see that there is no other or no more concentration with time or change in concentration with time, and thus I stop the pumping, right. And then maybe after a couple of months, let us say I come back, take the concentration of the relevant groundwater, I see that again the concentration is now higher. Why is that? Let us see the case, I guess. So, initially let us say the groundwater level was somewhere out here, right, and then after pumping has started, the groundwater, you have the drawdown, and this is the drawdown and the cone of depression, let us say, and so I pump this water out, let us say I pump this particular water out, let us say, right. But the key is that you still have LNaPl in this particular location. So, what have I removed? Only that NaPl that was dissolved in this particular aqueous phase or in this particular groundwater was removed. So, once I stop pumping, again the groundwater level is going to come back to its original level, right. Again the groundwater is going to be in contact with this LNaPl, right, and now again I am going to have equilibrium and thus transfer of what we say the mass of the contaminant from this particular non-aqueous phase to the aqueous phase, right. Again some of it will be soluble and that is what I see here, right. So, again different cases out here. So, what is happening here? I can think of the LNaPl as being stranded, let us say, right. I am pumping the groundwater out, let us say, but again maybe due to the what do we say capillary action, let us say, or because of surface tension, let us say, your NaPl though is not being pumped out though, right. It is present as a different phase and it is stranded now. Earlier NaPl was here, groundwater here, and I pumped the groundwater out, but NaPl is still stuck somewhere out here, and once I stop pumping, the groundwater again comes up here in contact with this NaPl, and now again I have contamination, right. So, again so these are the relevant aspects, or one more aspect where you would expect, let us say, a rebound of the relevant contaminant, right. So, let us try to summarize what we have looked at. So, one is the case when we have DNaPl or LNaPl, right. So, we can then have 3 phases, right, say, and between NaPl, soil and water, right. So, then there is a equilibrium between these 3 phases. So, even though you pump out the contaminant in this particular water, again you have a new equilibrium, and then that is going to be the case again, as in the contaminant can be transported from the NaPl into the H2O, or again from the soil into H2O, and so on and so forth. So, here it is limited by diffusion from the NaPl into water, or by desorption from soil into H2O, right. Again those are relatively slower process, right. And I think we also looked at stratification, right. We looked at stratification where we have different strata and thus different groundwater flow velocities, and I think we looked at stranded source, let us say, stranded sources, right, especially in the case of LNaPl, that is something we looked at, right. And we also looked at, I believe, let us say, when we have groundwater flow velocities being different because of the contaminant or the different velocities at different locations of this particular flow path, right. So, we looked at different cases when we are going to observe, let us say, tailing, and once we stop pumping, again rebound here, right. Again rebound is because I have different reservoirs of this particular contaminant. I mean, this is the concentration of the contaminant and time or volume of the relevant water pumped out here, time of pumping or duration of pumping, and here. So, the tailing, let us say, again different case of desorption and such, or stratification and so on. So these are the cases obviously when pump and treat might not be or will not be feasible, or practical conditions, let's say, are going to limit the efficiency. Obviously for that you need to understand the type of aquifer you have, let's say, right, because as you see it depends upon the type of media certainly, and also the phase of this relevant contaminant, as in is it mostly only in the dissolved phase or aqueous phase, or has it been adsorbed onto the soil, or is it also present as the NaPl, let's say, or in a different phase, right. So these are the aspects, so you obviously need to consider. So once I consider this, let's say, I obviously need to be able to estimate the time required for, let's say, pumping out a particular contaminant, let's say, right, because only then can I consider allocating the relevant resources. So let's try to quantify that. So here let's say I have, I'm trying to conduct the mass balance here. So the accumulation would be equal to in compound coming in minus compound going out plus anything that's formed or lost, right. So again this is just mass balance, right. So that's what I have here. So let's say I'll have rate of change of mass of that particular compound with time, let's say, is going to be, so once I start pumping, once pumping starts, I am going to assume that no other what do we say source of the relevant contaminant exists, so nothing comes in. So 0 minus out, how is it being pumped out? Let us say rate of Q, groundwater pumping rate, let us say, is Q, and the concentration of that relevant contaminant, let us say, initially is C naught, let us say, right. So the mass that would be removed will be Q C naught, I guess, right. Mass per time anyway, Q C naught, let us say, plus no reactions leading to forming or losing the compound, let us say. This is a simple case that I am considering obviously, right. So let us see what it is. So integrating this, what do I have here? Let us say I have dm by dt out here, integral, and Q C naught negative integral out here. So what will I have here? Mass at time t minus mass at time, so 0 to t and 0 to t, right. So again I am going to have what do I have here, please? Mass at time equal to 0. So this is the mass of the contaminant left after I pumped the water out for a certain time t, and mt equal to 0 is the mass initially present in the of the contaminant present in that particular contaminant zone. That will be equal to I have 0 here, so that is going to be equal to 0 here minus Q C naught into T, right. So that is what I have out here, and let us try to rearrange and understand the relevant terms, please. Integral 0 to T, right. So time for remediation is equal to, let us say, m time is equal to 0 minus Q C naught times T, right. So let us say this is the equation that I have, right. But let us say I want to obviously try to estimate the case when all the contaminant, or there is no more contaminant left in my particular aquifer, let us say, right. So at that point, what does that mean? So when time is equal to time of remediation, that means that the mass left at time t is going to be equal to 0, right. So after time of remediation has been reached, what am I going to have? I am going to have mt naught is equal to Q C naught T times remediation. So from here I can calculate the time required for remediation. So that is equal to obviously the mass that is initially present by the mass that I pump out, right. So here what I have a general calculation, let us say, for pumping the contaminant out. So what is this? I guess I have time required for remediation, right. And how did I get that? Obviously by assuming that at the time of remediation, or once I achieve that particular time of pumping, all the mass left in the particular contaminant zone is removed. So the mass left at time t is equal to 0, right. So the time required for remediation is equal to, what is this particular variable? This is nothing but the mass or total mass of the contaminant initially by Q C naught. What is the Q C naught? It is the rate at which you are pumping out, or removing the mass by pumping it out, right. So obviously here C naught will change, right. I mean the rate, I mean as you keep pumping out, the concentration of the contaminant in the groundwater won't be constant. Obviously it is going to change with particular time depending on the conditions. So obviously you are going to have different cases, I guess, right. But again, this is one way I can calculate that. So now let us apply this particular aspect, or let us say this particular generic calculation to the 3 cases, as in let us say what are going to the 3 cases we are going to look at. I am going to look at case when the compound is only in the dissolved or is only in the aqueous phase, right. And then I am going to move on to understanding what would be the case when it is in the dissolved form and also adsorbed onto, let us say the soil here, right. And the third case would be when I have it in the dissolved or in the aqueous form in the groundwater and also adsorbed onto the soil and also let us say as its own phase, let us say, or an NaPl, let us say, right. I mean there are different issues with NaPl, maybe this is something I should have made clear later, or pardon me, earlier. So NaPl, if the NaPl itself is a contaminant, let us say, it will obviously act as a reservoir of contaminants, right. But there is another case too, as in NaPl, if it is not a contaminant though, by being hydrophobic though, right, it can, what do we say, act as a reservoir for a contaminant which is hydrophobic, right. So again 2 cases, when the contaminant itself is, what do we say, present as NaPl, or when you have a non-toxic NaPl present here, right. So again think of this, let us say, you know, very generic example, because we look at K-octanol water partitioning coefficient or the octanol water partitioning coefficient. For example, let us say assume that octanol is present as a non-aqueous phase liquid there and you have that in contact with water, and the contaminant that you put in, let us say TCE, let us say, can or will stay in 2 phases. What is that now? Both in the groundwater and also in the octanol now, right. So this case though, where we are considering that octanol itself is not a contaminant, it still acts as a reservoir of contaminants, because this TCE or PCE, which is hydrophobic, would want to be in this particular non-aqueous phase, right. So there are different cases, that is something we are going to look at. So obviously we are going to try to first now work out the case when it is only in the dissolved form. So obviously how do I get this time of remediation? I know that it is equal to the total mass initially present, right, by QC naught, let us say, or rate of pumping here. So obviously I need to calculate the total mass present m at time equal to 0. So here what do I have now? I have an estimate about the concentration of the relevant contaminant in the groundwater, let us say that C or C naught here, let us say, right. I have the concentration of the contaminant in the groundwater and I know the volume of this particular contaminant zone. So if the total volume is V times porosity V, right, porosity times V, it will give me an idea about the pore volume filled with this particular contaminated groundwater, right. So I have here the volume of porosity times volume, total volume will give me the volume of contaminated groundwater, right. That times the concentration would give me the, what will that give me, mass of contaminant per volume of groundwater, right. So that will obviously, what will I end up with? I will end up with the mass of contaminant, right. So I will end up with the mass of contaminant. So in this context, if I try to calculate the time for remediation, what will I end up with? I will end up with time for remediation is equal to mt equal to 0 by, as I know, QC naught. So that is going to equal to epsilon V C naught by Q C naught, right, and then epsilon V by Q, right. And what is epsilon V? It is the volume of contaminated groundwater by Q, right. So what does this mean? It means that the time for remediation, as you can see here, is the time required to just pump out that particular contaminated plume, right. Epsilon V is the contaminated groundwater and Q is the rate at which you are pumping the water out, right. So again time for remediation is just as in this case, where we see that the contaminant is only in the dissolved form, right, say, right, it is only in the aqueous phase or only in the groundwater, right. So in that context, obviously if I just pump out all the groundwater that is contaminated, I am done with my particular case of removing the contaminant from the relevant contaminated zone, right. But now let us try to understand or analyze this particular case where we have the compound in 2 phases, let us say, both in the dissolved or the aqueous phase, pardon me, and also in the sorbed phase or adsorbed onto the soil, right. So let us look at that particular case. So we have this case where we have both the aqueous phase and also the compound adsorbed onto the soil, right. So here I need to calculate the total mass that is present initially, and how do I get that? So epsilon V C naught, right? That's simple because I know this is the volume of contaminated groundwater, C naught is the concentration of the relevant compound in the groundwater, right? Plus I now need to be able to estimate the mass that is adsorbed onto the soil, right. So, typically by relevant calculations, let us say it would, the concentration of the compound adsorbed onto the soil, the units will be milligram of compound per kg of soil, let us say, right. So, let us say if this is Q, right, thus I am expressing as Q, let us say, right. And what would this be dependent upon? We are going to look at that, but if we think of, I mean, we are going to try to express that in terms of variables. But if you think of the relevant aspects, Q obviously is going to be in equilibrium with the concentration in the water, right, because let us say if the concentration of the relevant compound in water is too less compared to the relevant equilibrium state, right. So, the equilibrium would want to shift this way, right. So, that is why I guess we do know that the compound, what do we say, the concentration of the compound in the soil is going to be in equilibrium with Kp is the partitioning coefficient with the concentration of compound in the aqueous phase, right. So, concentration of compound adsorbed onto the soil, will be in equilibrium. And how do I get that particular what do we say value? I get it by the equilibrium coefficient will be in equilibrium with my particular concentration of compound in aqueous phase, right. Here obviously I am assuming that it is what we say linearly, the linear relationship, but there are other ways to, or models too, I guess, right. Here I am just taking the simpler case, right, that there is a linear relationship between the concentration of the compound in the aqueous phase or the soil or adsorbed onto soil, pardon me, and the concentration of the compound in the aqueous phase, right. So, that is what I have out here. So, obviously I need to take that in. So, what is that about? I know that Q is mass of contaminant by mass of soil, right. That is what I have here, but what am I going to trying to calculate? Just the mass of the contaminant, right. So, I need to obviously be able to eliminate this particular term. So, how do I do that? I can do that by bulk density or dry bulk density into volume, right. Bulk density is the way I am expressing it anyway is the dry weight, let us say, by the total volume, and V is nothing but the total volume. So, obviously here dry weight or mass of soil. So, volume cancel out, dry weight and mass of soil cancel out, and I am just left with mass of contaminant in this soil phase, right. So, again let me write it down in a clearer manner. So, this is what I have, epsilon V C naught plus Q rho B into V, right. So, I can clearly express this or break this down further or simplify this further as I know Q. How is that, or what is that depend upon? It is obviously going to be dependent upon the concentration of the compound in the aqueous phase, as I can see from this particular relationship, right, because they are going to be at equilibrium with each other. So, Kp C naught rho B into V, right. So, typically though we are trying to understand, let us say, the time for remediation, let us say, right. So, that obviously as we know is going to be dependent upon the mass of the contaminant in the groundwater, right. So, to get an idea about, let us say, the extra time required for remediating the relevant what do we say site, if you have the compound in different phases, I am going to come up with a particular factor called retardation factor. R is the retardation factor, let us say, and that is going to be described as being equal to m time equals 0, the total mass divided by mass of compound or contaminant in water or in the groundwater, right. And that in this case is nothing but epsilon V C naught plus Kp C naught rho B V by epsilon V C naught. As you can see, this is the mass of the contaminant in water. So, that is going to be equal to 1 plus Kp rho B by porosity, right. So, if the contaminant is present in both the aqueous phases and the relevant soil phase, let us say, and let us say I am trying to estimate the relevant time required for pumping, the particular total contaminant out, it will obviously be dependent upon the mass present in the soil phase 2, right. So, to get an idea about that and the additional time required, let us say to pump such particular contaminated water out, I will need to look at the retardation factor. For example, let us say if the time required to pump what do we say only the dissolved phase out is 1 year, and I have case 2 when the compound is in both the dissolved and the or adsorbed onto the soil and the retardation factor is 10, let us say. So, initially if it took only 1 year, not initially, pardon me, in case 1 if it takes only 1 year, in case 2 if the retardation factor is 10, let us say, it will take 10 years for me to pump out all the particular contaminant. So, obviously we are going to try to quantify this or give some or assign some particular numerics to these particular values and calculate the relevant values so that it is clearer to you, right. But I guess I am running out of time, so I will continue this in the next class, right. So, again what have we been up to? We looked at the relevant cases for tailing and rebound, and then we moved on to trying to estimate the time for remediation, right. We did a simple mass balance, right, mass going out, let us say QC naught, and the rate at which mass was changing dm by dt, and we saw that time for remediation is nothing but the total mass present initially by the rate at which you are taking the mass out, right. And then we moved on to two cases, one where we looked at the time required to pump the water out when we have only the dissolved phase, right, and that is something we looked at here, only the dissolved phase, and we saw that in that case if I just pump out all the contaminated groundwater, I am done with the relevant remediation. But obviously if the contaminant is present in both the aqueous phase and the dissolved phases, because now the contaminant will dissolve from the soil into the groundwater if you keep what we say pumping the water out, I need to look at the relevant aspects. So, to consider that I came up with this particular factor called the remediation or not remediation, pardon me, the retardation factor, right. So, obviously the higher the retardation factor, higher the relevant what we say time required, as in if let us say Kp is high, right, if Kp is high, what does this mean now? What is Kp? As you can see, cube by C naught, right. Kp being high means this the fraction of the relevant contaminant in the soil, let us say, is greater than or is relatively higher compared to the fraction of the contaminant in the water, let us say, right, or the contaminant would prefer to stay adsorbed onto the soil rather than the stay in the aqueous phase, right. So, obviously in that case the time to remediate or pump out your particular contaminant will be relatively or remarkably high, right. So, again this is something we are going to take through in the next session, and for today I am done, and thank you.